Hello everyone, welcome to this evening webinar being hosted by the SOUM Scottish branch. I'm Ashley McGilloway, I'm the Programme Secretary for the branch, and I'll be chairing the session alongside Barbara from SOUM HQ and my colleague Charlotte Scott. Just a bit of housekeeping, if you're having any technical issues with the Zoom, if you could put a comment in the Q&A function and we'll try and sort this out. And secondly, after the talk this evening, there'll be time for questions. So if you could please use the Q&A function in Zoom as well, and we'll pose these questions to speaker at the end. So this evening, we have with us Dr. Hamish Moore from CBEC Engineering, who will be presenting on sustainable approaches to river engineering and management, showing some practical examples of best practice working with river processes. Hamish has more than 25 years experience working in the water resource industry in the UK and in the US, both in research and in consultancy capacities. Particular areas of expertise are process-based catchment management and river restoration, design and construction. His research interests include the interactions between geomorphic processes and freshwater ecology and the catchment scale prioritisation of natural flood management measures. Dr. Moore has been active in promoting more sustainable approaches to river restoration, recently co-authoring 2 high-profile papers on the concept of process-based restoration. And as we all know, working in the water environment, engineering works are often required where built infrastructure, such as road, railways, tracks, pipelines, cables, buildings interact with rivers and their floodplains. Activities such as flood walls, bank protection, dams and weirs, amongst other things, are all common in relation to flood risk reduction, scour, erosion mitigation. And while these works must deliver a functional outcome, there's an increasing requirement that they're sustainable in the longer term and sensitive to the natural environment. And such objectives are best achieved by the approach that Hamish is going to talk us through this evening, with looking at solutions that aim to reproduce and reinstate the natural form and function of a stable-based floodplain system. Hamish will describe the background to such an approach, as well as the advantages of its application, and provide examples and design on construction methods, including case studies, both successful and unsuccessful. So without further ado, I'll hand over to Hamish to lead us on our talk.
Thanks very much. That's a really good introduction to what I'm going to talk about. I hope I cover all those issues. There's quite a lot to cover, I guess, because my title is looking at the sustainable management and engineering of river systems, you know, river management and engineering covers a whole range of issues, and I'll try and cover much of these in this talk. One of the topics I'm going to try and focus on a little bit to begin with is river restoration, which is really for primarily for an ecological objective, but has got lots of additional benefits that will become apparent. But then I'll focus more on the more traditional types of engineering that will that are used to protect assets, etc., and focus on more sustainable approaches to those. So it's really a sort of a means to come up with a strategy for a more sustainable management of the entire river system. So the talk outline, I'm going to go through an introduction to sustainable river management and engineering, some examples of the types of things that can go wrong in some settings, and I'll give a few examples of those through the talk, and then a section on appropriate channel design. So to introduce the sort of general approach to this, and then go through some examples of stable channel design, going through the sort of a continuum of varying risk, types of river environment and different objectives. Like I say, I'll try and focus initially on looking at objectives for ecological benefit for river restoration projects, but showing that these also have additional benefits to other aspects of human use of rivers as well, and then start to go through some more traditional engineering objectives and showing how these can be done in a more sustainable way. Like I say, yeah, example would be sort of bank protection works. I'll give some examples of those. There's an awful lot of potential examples I could give. Because of time limitations, I'm not going to be able to go through all of the various aspects of this. I'll try and focus on the ones that are perhaps most relevant. Why do we, why sustainability? CBEC's tagline is design with nature, and that's really what we're trying to do here. We're trying to work with river processes as opposed to resist them. So it's just a concept of nature-based solutions, working with rather than resisting river processes. And these days maybe the term rewilding is relevant, but it's maybe not the most appropriate term for what we're describing here. But it's the same. It's the concept. You're working with river natural processes as opposed to resisting. And the advantages are that it enables a more sustainable management of the river environment and recognises the natural capital of the river environment, the intrinsic value of the natural environment for human life. And through these approaches, we provide improved resilience to river systems, specifically in relation to climate change. Often as well, these types of approach working with natural materials result in a sort of carbon neutral or even a carbon negative solution where we're actually storing carbon. A lot of these river restoration approaches will, especially when we're restoring wetlands and peatland environments, actively restore carbons. They have a carbon negative benefit. And also biodiversity, again, is increasingly a metric that we're using to apply to these projects in order to identify their benefit. So as a general background, I would like to give a bit of a context to this in terms of fluvial geomorphology or perhaps hydromorphology. This sort of forms the background to the sort of work we do. It's all of this process-based or nature-based approach is based on an implicit understanding of geomorphic processes, physical river processes. So just as a general summary of what geomorphology is, here's a rather dry definition of it. It's a science relating to the understanding of the evolution of the physical forms of rivers and their floodplains. This is an important understanding. We need to incorporate this understanding into our management of river systems in order to derive or develop appropriate solutions. So the important concept that we or the processes that we're trying to understand here is the transport, storage and deposition of water, sediment of all sizes and wood. Now it's these interaction of these processes which defines the physical condition of river systems, and particularly as geomorphologists we're interested in sediment. So it's the supply, transport and storage of sediment really that's fundamentally related to river management. And one important aspect of this the sustainable management of river systems is implicitly understanding that rivers are dynamic environments. We have to incorporate this idea of dynamic behavior in river environments in order to come up with sustainable solutions. So this is an example here of showing why that's important. This is the River Drury near Aviemore, tributary of the Spey. This is the most recent Ordnance Survey map of the site, and here we sort of, this is an old distributary channel of a historical braid of the River Drury. And as a geomorphologist, that starts to make you think about, how dynamic the system is. If we go back in time and look at the first Ordnance Survey map of the site, 1903, the river is pretty much in the same situation as it is now. But drawing the dots between those two, you think, oh, it's quite a stable system. But if we focus in on this section here, if we go to the 1971 map, we see this very, very different environment here, where we've got this historical braid is active in this time period here. So what's happened at some point between 1903 and the most recent Ordnance Survey map, we got this avulsion event and the river jumped its course into here. And that's a process that periodically happens. So looking at these sort of historical assessments provides us this understanding for the potential for dynamic behavior, and different environments behave in more dynamic ways. So incorporating that potential for dynamic behavior is very important. And this is the same site here, looking at that location on the River Drui near the Coilen Bridge Hotel. This is the site as it looked like in February 2015. And without any very significant flood events, this is how it looked in February 2016. So, you know, a very dynamic system that we need to consider and incorporate in any measures or management or engineering of the system. We need to incorporate this potential for change within the measures that we promote. Many examples of the failure of consideration of geomorphic process, and I'll give a few examples here. Here's an artificial channel that's a gravel riffle has been entirely removed. It's been scoured to bedrock because of a failure to consider geomorphic process. Similarly here, this is an example of a meander bend cut off. A nice sinuous channel was designed, and very quickly the river cut through the back. Again, failure to consider geomorphic process. And here's a fairly classic example, an example that's provided in, I've seen this in many talks now, but it's a photograph that John Buffington from the US provided me. It's a design channel, a nice classic meandering channel that we might regard as being the ideal form, but without an understanding of geomorphic process, the design was inappropriate. And after the first flood event, we see the river returning to this fairly typical environment for this setting, which is in California. So the river's moved away from this meandering plan form to a more braided system, which was its reference state. So a failure to consider geomorphic process results in these types of failure. Another example here, quite often in steep channels, we'll propose putting in what are called step pool channels, and I'll give an example of one of those later. And here's one that's failed to consider the appropriate geomorphic process. So because of the wrong dimensions of the step pool channel, the steps have been undermined and outflanked by the river process. So it's obviously a fairly significant failure of a design. This is a good example that I often use in these talks about how failure to consider geomorphic process results in failure. This is a very small tributary of the River Don near Aberdeen in Dice. It was a previously culverted channel that was daylighted along this red line here. So it was for housing development. And to maximize the space for housing, the channel was pushed right up against the border of the site, and in doing so they created this very steep, up to about an 8% slope, this steep ditch. Very simple trapezoidal channel cut into unconsolidated sediments, ripe for destabilization under a high flow event. We tried to advise the contractor that this wasn't going to be a stable design, it wasn't appropriate for the site, but he didn't really sort of want to listen to that until I think it was about 7 days after this photograph was taken. They got about a 10-year flood event, and this is what happened. A very significant erosion event, obviously. So there was a head cut that began at the bottom end of the site, and the erosion zipped its way all the way up. Here's a sort of waterfall feature here. So it lost a massive amount of sediment in one flood event. And this is what the head cut looks like. So fairly classic, sort of very active head cut. And you'll see the material that the river, the burns cutting into, the very sort of loose, unconsolidated material, very highly erodable. And this continued over subsequent events. So this plot here shows, how much material was liberated. So all of the area underneath this pink line, which represents the original channel, represents a level of erosion. And you'll see the progression of this head cut. This is it happening, moving up about 10 meters in the course of one flood event. So very significant destabilization and massive liberation of sediment downstream as a result of that event. And that head cut continued. It continued past that waterfall feature and zipped its way right up until it picked up the old culvert here. It's the hard point that it couldn't go any further, but everything upstream of that was eroded. So a significant failure. I'll come back to this one to show you what type of approach we use to resolve this situation. So I've mentioned geomorphology is really super important in incorporating appropriate design, but how do we implement this? How do we understand geomorphology at the appropriate scales in order to direct the design? And often, like I've shown before, historical assessment is really useful for understanding the potential for dynamic behavior of a river system. Also, a walkover geomorphic survey, often called a fluvial audit, is really useful, and it provides this general physical context of the site you're interested in within the larger catchment. So you rather than just getting a snapshot of what the condition of that site is, you can fit it within the context of the river system to get an idea for how the river is operating and the nature of geomorphic process that's apparent. And you gather this evidence, you gather, a range of indices of indicators of geomorphic process, and you come up, this is going back to the River Drury again, and you can come up with the spatial maps like this, identifying the spatial distribution of key features. So we'll have, you'll record things like, storage of sediment as alluvial bar features, and other areas of major sediment accumulation of bar complexes, where large wood materials accumulating. We'll record information on different types of channel, different morphological channel types, and also things like existing engineering, for instance, different types of bank protection or embankments, and degrees of erosion. Erosion being an important source of sediments, which is contributing to geomorphic process. So through this sort of assessment, we build up a picture for what geomorphic processes are operating at the site. And then if there's, a particularly risky issue that we're dealing with, often detailed numerical assessments will be employed. So in the extreme, hydraulic or sediment transport modeling can be used to refine a design, but also more simple equation-based, regime-type geomorphic relationships or hydraulic geometry type relationships can be used. But these sort of numerical assessments can be used to iterate towards a stable design, and the end product being this stable channel design that we're aiming for. So the fundamental design approach is that we're trying to incorporate in sustainable river management or sustainable river engineering is to reproduce natural physical processes as much as is practicable. And this is the designing with nature concept, or the tagline that we like to use. And fundamentally, as much as is practicable and possible, we like to allow the river to do the work. The river knows best; it's the best architect of its stable form. But we have to address that against risk. So if there's risk to property or services or infrastructure, that dictates how much freedom we can give the river. But as much as possible, we let the river do the work. And this approach is likely to produce a more stable environment, and it's more sustainable. Provides greater resilience to climate change, and is more environmentally sensitive in the sense that we're using natural materials. We're using less, materials, concrete, etc., that have got a bigger carbon footprint associated with them. Importantly, they're much more likely to be approved by the regulator. The EA in England and SEPA in Scotland are very much on board with this working with river natural processes approach, and any design approach which incorporates this philosophy is very much is a much easier approach to get designs approved or licensed. However, it's not a one-size-fits-all approach, and as I identified before, the geomorphic assessments are critical to identifying the appropriate type of design for a given environment. So you need the appropriate level of assessment and design for producing the appropriate design. But one general rule of thumb is that channel gradient is very important. Channel slope is perhaps the most important variable when identifying the appropriate type of approach for a given river environment. So I'm going to give some examples of the types of works that these can relate to, and I'm going to start off with more river restoration type of approaches, I want to give examples of the more rewilding end of the spectrum first, to show what the type of things that are possible taking that type of approach. So this first example it's for ecological benefit. It's a rewilding type of project, and it's basically removing the artificial constraints to natural river process and let the river do the work of recovery. So it's a stream, the Altlorgie in the Cairngorm National Park, and it was managed for years by the local farmer to dredge material. The river wasn't really doing what it was meant to do. It was going all over its floodplain and causing problems. So the river was dredged, and that dredged material was piled up against its bank as an embankment to train the river into a certain location. So the design approach was very simple. It was just a case of removing the embankments, adding some large wood material into the channel to kickstart process, and that sediment that was taken from the embankments, because it had originally come from the channel, was put back out into the channel upstream to kickstart sediment transfer process to begin this trajectory of recovery. And sure enough, after a few years, we have this much more natural environment. And this is obviously, aesthetically, a good outcome, and it's a great outcome for in-stream ecology, but the secondary benefits are also significant as well. The river's much better connected with its floodplain now, so there's natural flood management benefits in terms of more floodplain storage of floodwaters, and there's actually a much better benefit to agriculture through better drainage, because the river's finding its more appropriate path, a lower elevation bed generally, and field drains are able to fall much better. A similar type of project is with a little bit more constraint, was a project on the River Nairn near Inverness. Here, an obviously straightened channel, but with a very high sediment supply from upstream that our geomorphic assessments determined. Over time, the river bed was aggrading. The bed was continually raising, which required embankments to be continually built up to stop the adjacent land from flooding. So this was really a project that was related to land management. So we wanted the landowner wanted to manage the sediment coming through the system to improve land drainage, again because of the elevated nature of the channel. The field drains didn't have any fall on them, so it was and there was also associated flood risk issues as well. So the design was to realign the channel into a more appropriate location, using large wood structures to kickstart channel evolution. And again, over time, we result in this much more physically diverse environment, which has significant ecological benefit, but again, also had these secondary benefits for improved land drainage, because a better fall in all the drains, a much more sustainable environment where the river didn't need to be dredged anymore. The sediments are naturally stored within the channel. And again, much better storage of floodwaters on the floodplain in a more natural sense. There's a natural flood management benefit also. Another example of a similar environment that we're working on just at the moment, and I just want to add this one in. Really, it's not a project that's been completed, but it's an example of peatland restoration. And peatland restoration is obviously a major area of work at the moment, and there's just very little really understood about peat channel restoration, and this is something we're trying to move into. So this is an environment here. It's also a ditched channel in a peatland catchment, and it's really purely for ecological benefit, this project. But you see a sort of aerial view here of the artificial straightened channel here, but quite obviously you can pick up the old sinuous channel. So the idea here is to reinstate the channel. So if you can pick up this light alignment here to reinstate these natural peatland processes, to reinstate the natural hydrology of this peatland environment, which is what, you know, is the hydrology that maintains the peat environment. And it's for the objective specifically. I don't know if you can see in this photograph, it's for the objective. It's a purely ecological objective for the benefit of power mussels. You see at least 3 power mussels in the photograph here. But it's an example of where this type of approach of reinstating natural process is relevant. And peatland restoration is a significant one we need to work on a lot more. Another example here, a bit more constraint here. We've obviously got a major highway here, but this is the Eddleston Water and the Scottish borders, and this was again, it's a project that was had natural flood management benefit. It was trying to reconnect the channel to its floodplain to improve flood storage on the floodplain and protect downstream. It was, you know, the town of Peebles is downstream, and it's to provide some flood benefit to people. So initially the channel was absolutely dead straight like this for about 3 kilometers, and the design was to reinstate this more natural sinuous plan form and reconnect the channel with its floodplain. So we conducted various hydraulic modeling exercises to aid in the design of this. You see this output here, there's this section in here we're looking at. And this was really to sort of identify the sort of frequency of inundation and to ensure that we could protect certain areas of land. For instance, this field here was of critical importance to the farmer, so any designs had to involve the protection of this from a particular size of flood event, which the model here shows. And sure enough, under flood conditions, this is the site flooding. This is going from upstream to downstream, and here's the corner of this field here protected. So you see the flood risk benefit of all this water stored here, but certain critical areas of agriculture remain protected. So this is the river as was, you know, very straight, you know, but ecologically simple. This is under construction, and this is the same site after a couple of years of evolution. You can see the potential ecological benefit, but also the benefit to flood risk in terms of the added floodplain storage, and at the same time the significant infrastructure is protected also. This is going back to the previous example I gave, the mains of Dice Burn, the tributary of the River Don. This is the sort of canyon that developed after the flood event there, and the design here was to reproduce the natural morphology that would exist under these sort of imposed slopes. So when you get slopes of greater than about 3%, this natural stable morphology that a natural river will take will be a step pool type of channel. And that's what we try and reinstate. So we use this type of relationship here. This is an empirical relationship which just describes how natural channels, how their geometry adjusts to a stable condition. So we produce a candidate step pool profile here. This is the sort of the long profile of the design. We conduct some hydraulic modeling just to ensure that any material that we use, the boulders that we use to make up the steps, are going to be stable. We need to understand what the maximum forces on them are. That allows us to produce some detailed designs that are supplied to the contractor. And this is what was built as a, you know, to replace that eroding channel. So here we have the sequence of steps. We've also widened the river, or the Burn corridor, a bit, so there's more space over which to spread the flow more, so there's less force acting on the bed. And this is it, obviously shortly after construction, and this is it a couple of years later. There's been some larger flood events than caused the initial erosion, but you'll see the channel's now entirely stable because of the, applying the appropriate type of morphology. This is it looking upstream again shortly after construction, and this is it about 18 months after, and this is it more recently. You'll notice the risk here. I mean, this is the reason why we had to employ such a why it was important to ensure a stable design. This is the closest property to the channel. So under the previous eroding channel situation, this property would have been quite at risk. So this is the risk we had to deal with in this example. It's not for ecological benefit in the slightest. The water quality, as you can probably tell from the staining on this sediment here, is really, really poor. It's draining an industrial site upstream. So there's no ecological objective to this. It's purely for producing a stable channel design. Another example of an application of a step pool channel was the green burn. This is a project which we had called the Aberdeen AECC, the Aberdeen Exhibition and Conference Centre, but it's now changed its name to P&J Live, which I can't quite get my head around, but that's what it's called now. But again, this is the channel under a stable condition after the design has been implemented for a couple of years, and you'll see it's quite closely associated with the building, associated with the P&G Live structure. But the inherited design, we got involved in this project sort of halfway through the design process when SEPA had some concerns with the original channel design. I'm not sure what this was meant to be, but this was the initial design which we inherited, and we were asked to see if we could come up with a solution. So there was concerns with an appropriate channel morphology for the realigned channel, and also channel stability. And the reasons for channel stability were these three sections here, which were over 3% slope, and there was no step pool design in what had been implemented. So already there's a concern that those sections of channel aren't going to be stable. And the potential of a head cut, the similar sort of thing that happened on the Mains of Dice site potentially could happen here. So we were asked to conduct some sediment transport modelling, which we did. And this is the output here. So the sediment, here's the steeps, one of the steep sections of channel here. Red indicates erosion, blue deposition, and over the course of a flood event, I'll show the sequence of erosion developing, and you'll see these reds migrating their way upstream. And this is a migrating head cut. So this model, the sediment transfer model, is predicting a migrating head cut, which is suggesting instability of the design. So this wasn't an appropriate design, and we developed an alternative step pool design, much the same as in Mains of Dice, using this type of form here. And we reran the model for the step pool design. And although there are some localized patterns of erosion and deposition, generally the design is stable. There's no systematically upstream migrating head cut anymore. So we produced an appropriate design for that type of channel, that slope of channel. And this was implemented. Now, there was another problem because the channel had pretty much been built already by the time we were able to revise the design. All of the channel margins had been turfed and geotextile had gone on, so there was an unwillingness to go in with machinery to fix the design. So all of the steps had to be constructed by hand, which meant that you couldn't use big enough boulders to key into the bed to provide stable steps, given the forces, the hydraulic forces under a flood event. So there was a fairly significant flood event that occurred, and you'll see the sort of the height the flood got to up to about here, and it did take out some of these steps. Some of the steps were damaged, because they weren't implemented correctly first time round. And sure enough, this did result in a head cut. This is the exact area that the model predicted a head cut. And there was about 0.5 metre of incision of the bed, which exposed this liner here. And so we had to go back in again and get some machinery in to fix this section of the design. So this is the same section again, with a more appropriately sized step boulders put in place up through the rest of the design. And then after another 18 months or so, you'll see it's entirely stable now, and it's vegetated up really nicely. So with an appropriate consideration of process and appropriate construction methods, we can produce a stable design. And I wanted to touch briefly on the sediment transfer modelling again. Sediment transfer modelling was absolutely critical in the design of that last project, the AECC, or the P&G Live project. And it's a very, very useful tool for us. It's becoming increasingly useful for us in identifying appropriate designs. Sediment transfer modelling really is a numerical synthesis of geomorphic process, and it's really, really useful. This is an output from a sediment transport model here showing predicted erosion and deposition at a location where we're removing this weir. We're in the process of finalizing these designs now, but we need to understand what happens when this weir is removed, and this is the output. So this is showing erosion here and deposition downstream. And we need to sort of iterate this design to try and minimize the difference between the erosion and the deposition to manage flood risk and channel adjustment. So it's a very, very useful tool for understanding how we, looking at different design options and iterations of the design. It's sometimes regarded as a bit of a black art, and this is a good example of validation of a sediment transfer model. So this is on the Eddleston Water, and this first plot here shows surveyed differences in channel topography subsequent to a flood event. So this is surveyed, this is actually measured differences, erosion in the yellows and reds and blue in the deposition, and this is the same flood event modelled. And you'll see very close correspondence between the two. There's really good validation of the potential. If you have the good enough data being used as input to these models, it can produce really quite realistic output. So we're really reassured that these sediment transfer models can predict accurately. I'll quickly run through this example here. This is another example of a project with significant constraints. It's the East Tallis Burn project in Aberdeen City, and it was an example of where there's significant constraints relating to underground sewers and power supply and public path networks. So there was a general concern with water quality. It's a public park. There was misconnected sewers upstream and the industrial site upstream. There's a very, very poor water quality coming down this burn, and that in flooding situations was inundating these public areas, football pitches and play parks. Also, flood risk was impacting public immunity. The path network was getting significantly impacted. So this is a model output of the existing condition. The flow is going from left to right here, and you can see the inundation. It's a relatively small flood event, but you can see the inundation which is impacting these sort of play areas and the path network. And so the design was to utilize the existing conditions to the extent that this inundation area here we sort of altered into like a online water quality treatment pond with appropriate wetland plant species in there. And then we created a more sinuous, naturally sinuous channel, a two-stage channel. So we've got this, the dark blue is like a low flow channel, the light blue is an inset floodplain. And then this offline, another offline wetland area here to store floodwaters and also to provide water quality benefits. And through this, because the floodwaters are contained within this inset corridor, we managed to reconstruct the path network to allow sort of public access not to be hindered. So these are the designs we produced here, and this is the site as constructed. So whereas this is the same photograph here, pretty much the same goalposts. This was the nasty canalized ditch with obviously the evidence of poor water quality. And here we have this sort of two-stage channels, this sinuous low-flow channel set within this inset floodplain. This is shortly after construction. There was a lot of planting done. This is the planting taking hold. This is after the end of one season, and this is it last year. Obviously with the issues of the high nutrient content in the water quality being so poor in inverted commas, the vegetation really took off, and it's become, rather than a two-stage channel now, it's become more of a wetland, which isn't necessarily a bad thing in terms of ecology. This is the site looking from the hillside looking out to sea. This is the path network that used to get flooded. You'll see the flooding over here. In flooding, it would extend over the path. Here's the burn down here. This is it during constructing these online wetlands or offline wetlands. This is it just after construction, after the vegetation's taken hold, and this is it recently. And if you focus in on this area here, this is one of these wetland ponds now, so providing excellent amenity for the local wildlife, and a lot of bird species which never been there before being identified by the local park ranger, and these areas as well providing excellent water quality benefit. I wanted to go through some other measures. This is moving away from the sort of river restoration, river management side of things, moving more towards the specific bank protection measures that are just the example I want to raise about how we can employ different approaches and different more sustainable approaches to protecting assets, and specifically into protecting assets in relation to bank erosion processes. So traditionally, riprap, or rock revetment, or boulder placement, or gabions has been used. And it's they're traditional but not natural, and there's significant carbon footprint associated with these measures, and they often don't work. And I'll give some examples of the ways in which they don't work. Required in some locations, I would say I'd put a question mark against that, because I think there's always an option for something a bit greener, a bit more sustainable. I don't necessarily think that a purely hard engineered solution is necessary, but I'll go through some examples to show you the sort of things I'm talking about. So the alternative that we are increasingly using is large wood structures, using large wood structures to provide the sort of superstructure to protect banks. Advantages is they're natural materials, they're more effective at energy dissipation, and the complex structure of the wood structure. So we always retain the root plate, and the root plate's facing the flow. The complex structure of the root plate dissipates energy through turbulent forces. So rather than just deflecting the erosive force like a rock structure will, it actually actively dissipates. And it's plastic in the sense that these structures will deform with the bank. So the bank has got some room for adjustment. So this is the sort of working with natural processes. I mean, banks will naturally protect themselves with large wood. When you get wood ingress from the riparian areas, that will often, and typically does, provide natural protection to the banks. And the banks deform with these structures, that they become part of the bank. A problem typically, though, in terms of application, is the sourcing of the large wood structures. We're basically requiring whole trees with the root plate intact, and you can't really go to Travis Perkins and buy a dozen of those. You've got to have a local source of large wood, like a local plantation with some windblown trees, etc. That's the biggest issue, really, and this transportation of those large trees to the site, which is often problematic. And it also requires some bank space in order to implement these structures and bury them into the bank. It requires some bank space. So typically at least 5 meters of bank needs to be available to integrate these structures. So in some locations that's just not possible. Sometimes, you know, you might only have a metre of bank space, and an alternative approach needs to be adopted. So here's some examples I want to give. I'm going back to Drury again, lots of examples of the Drury here, but some examples of why traditional measures don't work. This is the Drury. There had been a significant flood event which caused this bank erosion here, presenting a risk to these chalets. And so a fairly traditional riprap protection was put in place. Looks fairly resilient. The river's never going to damage that. You know, the river, there's not enough not enough force in hydraulics to physically pick up those stones. But what does happen, the river is not able to migrate laterally anymore because of the stones there. So it does tend to erode the bed instead. And you can, I don't know if you can see, but there's a sort of dark, deep channel here developing. And in the downstream end, this has resulted in the undermining of the riprap, and it falls into the channel. You get, you know, the rocks become stranded in the channel, and the erosion process picks up again. So gradually this structure becomes undermined as this you know, scour hole here migrates its way upstream, and the rocks drop in. So in a dynamic environment like the Drury, this type of large rock is really inappropriate. I mean, almost invariably over time, these large rocks will end up in the channel and the river will get behind them. Another example, this is the Eddleston Water in the Scottish Borders. Again, riprap used. So it's a fixed bank and it's not permitting natural river process. So again, the river's wanting to migrate. You see that from, you know, this bar developing, the river's trying to migrate into this bank here. It can't migrate laterally. So if you look at this location here, again, the same thing's happened. It's undermined these rocks and they just fall into the channel, and then the river gets in behind once the rocks have been undermined. So not a sustainable approach. Sheep piling, same things happen. Again, this is a dynamic river. This is the River Wharfe. Here we see a very significant alluvial bar feature here. The river is trying to, you know, where you get these alluvial bar features, the river is being pushed over to the opposite bank, trying to erode here. And what it's done is undermined this significant sheep piling that's protecting this golf course, and it's failed again. Similarly with gabions, here's some gabions in combination with large rock that have, the river's got in behind the large rock and, you know, pulled the gabions away. So all of these hard protection structures and these dynamic systems, dynamic river systems are prone to failure. So the alternative that we've employed successfully is using large woods. So here's an example of on the river, Mainstem River Dee, so a large river. And this was a design, this was a traditional riprap design that was put in unlicensed, that SEPA required to be removed because of the, you know, protected, the SEC status of the Dee, the protected status. They wanted something a bit more appropriate, a bit more sustainable and environmentally sensitive. So this is the, believe it or not, all the large wood structures are embedded in the bank here, and this is the channel subsequent to the large wood structures going in. So one big question that people worry about is the stabilization of large wood. Obviously wood is buoyant. How do we stop it moving? So there's various approaches we employ for that. So using whole trees, or at least trees with root plates still intact, is important. Using large enough trees relative to the size of the channel. Also using sufficient amount of wood. So you create structures that, you know, a lattice work of wood. So the wood is stabilizing the wood is another approach. And this is really just following the ways in which these structures naturally become stabilized in you know, how rivers naturally stabilize themselves. Also orientating the wood appropriate to the river flow is significant. You know, the root plates tend to be facing into the flow, at least at some, you know, at least at 45 degrees to flow. It's important in providing stabilization, and to partly bury the wood structures into the bed or bank of the river and backfill with appropriately sized material ballast to resist buoyancy and drag forces. And a last resort, although we never really have to do this, we often have to do this just because people don't feel confident that these structures are going to be stable, despite our evidence that they do stay stable, is using cabling or anchors, more sort of engineering approach to stability. And often, if people are really concerned about the stability of structures, we'll assess what's required to stabilize them, conducting some fluid dynamic assessments for assessing stability. And this is the type of feature that we're looking at to produce. This is in cross section, so we'll use these root plates intact and as typically at least a 5 meter length of trunk, integrated into the bank, with the voids between the trees filled with coarse material, so 50 to 200 millimeter size material, and then boulders used as ballast to sort of hold the structures in place. So there are rocks used in the structure, so it is a sort of composite. It's not just wood that's being used. The rock is not presented to the flow. It's not the main means of protection, but it's being used as ballast to stabilize the wood structures. And then in plan form, you'll see the orientation here. So if this is the bank of the river here, the river's flowing this way, this is the approximate orientation that the wood structures will have. And for a high bank, you might have 2 tiers of these wood structures offset to one another, and and a significant proportion of them buried into the bank. So an example here of bank erosion. This is again Neddleston water. This is obviously bank erosion that's impacting this track here. And here's the wood structures going in, root plates presented to the flow. This is it shortly after construction. You'll see the coarse gravel cobble material that fills the voids in the base here. And this is backfilled with this material, and then topsoil and planting. And then after 1 year, you can hardly see the structures. You see one of the roots here, but they've become integrated in the bank. They're sort of living part of the bank. Much better biodiversity gain. There's a very significant biodiversity gain to these types of measure, but they're doing the job as well. They're protecting the bank in a much more sustainable way. These are the types of structures we're implementing. The root plate is very important. Retaining as much of the root plate as possible is important, and at least a 5 meter section length of the trunk as well. So these are typically trunk diameters at least 300 millimeters and bigger. The bigger the better, really, especially for larger water bodies. And here's an example of a 2-tier structure getting implemented. And here you can see the cobble gravel fill between the voids, between the trunks going in. And there's, I don't know if you can see it, but there's like a lower tier than an upper tier of these structures, and this gets backfilled. So this is the example on the D. This is the hard rock that was there initially. And this is the large rock getting removed, and it's stored because we're using that large rock as a means to protect the bank, to stabilize, to provide ballast to the wood structures. Here's the wood structures going in place. They're put in about 1 to 2 meter centers. Where the trees aren't big enough, you'll see here we double up, so we'll use 2 or maybe 3 trees if the trees aren't individually big enough. And then here's these boulders going in to provide the ballast to hold the structures down, and then the backfill of this cobble-sized material to fill the void spaces. Here's a line of the trees here going in, and this is a sort of wall of rock material that gets integrated into, in this case, got integrated in the bank to sort of hold the structures down to make sure they weren't going to move. And then topsoil, and then geotextile also, the soil seeded in the geotextile going on top. And then this is again after 1 year. So the structures, are integrated in the bank, and compared to the original design, you can see, a much more I would say attractive design, but also providing a much more sustainable means of protection of the bank. And over time, with these wood structures, are a living part of the bank, and before too long, these willows started colonizing, and with the the bank left to recolonize, very quickly you have this, living bank. It's like it's a naturally sustaining protected bank. Another example in a sort of different environment, again, it's a peatland environment. This is a eroding section upstream of a bridge in Sutherland. This is pulling the peat back. An important thing here was retaining the peat so we could reinstate it. So this is pulling back to the sediment, and then after reinstatement, just as you can see the proportions of portions of the root plate sticking out of the structure here, but we've put the peat back in and reprofiled to an appropriate stable angle. And as a final example, this is a fairly extreme example. This was where we really are needing to protect an important asset. This was a high pressure gas pipeline, I believe. This is a Salix, as you can tell from the logo. This is a Salix design. So it's using rock rolls and willow stakes and brushwood mattresses as a means to provide a very resilient level of protection for a high-risk asset. Here, the rock rolls are going out to provide toe protection to the bank, and then held in place with these fairly large diameter willow stakes, live willow stakes. They take off pretty quickly, and then over this bank's reprofiled to an appropriate angle, and then this live willow brush is put in over the top, and that's here you see the live brush mattresses going over the top of the slope here, and then they're pinned in place with more stakes, and the stakes going in here. So it's a layered process of a sequence of the rock rolls going in, held in place with the stakes, the brush going in top, more rock roll, more stakes. So this is built up, and this is the finished product here. And then after a year, we have this natural living bank with a very, very high level of protection that's actively dissipating energy, and providing some ecological benefit as well. And also it's got a very, very low carbon footprint. There's rock roll used here, but the amount of growth that you get from the willow and the use of the wood, it provides a carbon neutral or a carbon negative situation compared to using concrete or large rock. And I think I have rushed through this talk, and it's maybe I've gone maybe slightly over the intended time I was hoping to, but I think that is my last slide. Apart from just to go over some of the take-home points, I think to summarize, and I think one of the take-home points really was to identify or to stress the multiple benefits of employing the sustainable approach. So it's not just you've got a specific issue you want to deal with, but by applying these nature-based approaches, there's also multiple benefits, or typically multiple benefits, of allowing the river to reinstate natural process. If the ecosystem services of a river functioning naturally provide multiple benefits, not just the environment, but also to human activity. It's key to understanding river processes. The understanding of river processes is key to successful design of sustainable, stable river engineering. I can't really stress that enough, how understanding the nature of your river is critical to applying the appropriate management or engineering solution. And a critical aspect of this understanding is acknowledging that rivers change their dynamic environments, and change dynamic process must be considered in design. We can't expect rivers to be static, and if we do consider or try and make rivers static, things will fail. The river has a requirement to be dynamic. We must consider that. And as a general concept, that underlies all of this, reinstating natural river process and form is the most effective design strategy. Reproducing the form and process to which a river would naturally be stable is the way to address these issues in a sustainable way. But again, to stress that it's not a one-size-fits-all approach. Different types of solution design are required in different river environments. And depending on the degree of risk that may be presented at a site, different degrees of assessment may be required, and that might include hydraulic modelling, or indeed, as I try to highlight, the value of sediment transfer modelling, I think is a very powerful tool for managing the risk and producing a sustainable design. And just as a final takeaway point, I guess the last few slides I presented about the large wood protection, although rock is suitable, I would always consider asking the question whether large wood structures are appropriate, because they're much more sustainable in the longer term. They are much more resilient to change, to the dynamic river processes, and they have a much smaller carbon footprint. In fact, as I said before, they can be carbon negative. So, where possible, implementing large wood structures, not just for bank protection, but for providing ecological enhancements is I think a very valuable methodology that we can use in river management. So yeah, and that's my talk. I just want a quick highlight that we're recruiting at the moment. So we're looking for geomorphologists to support our team at the moment. We've got an increasing amount of work in this area. It seems like working with natural river processes is something that's really piquing the interest of our clients, and we're really sort of developing this area quite significantly at the moment. So yeah, we're always looking to find the right people for our team. So if it's not too inappropriate, I would suggest dropping me an email or a phone call if anyone's interested in having a chat about a job. And yeah, just to say thanks for SciWim allowing me to ramble on for an hour about the sort of stuff I find really exciting and interesting.
Well, thank you very much. That certainly was very interesting. I've certainly learned a lot and find out about all the different approaches. So we actually have quite a lot of questions which have come through. So I will just sort of fire away and ask them one at a time for you. And yep, so the first one is how do you engage with riparian owners, responsible parties on watercourses that cross boundaries? There is no point in repairing one reach to only potentially pass the issue onto a downstream neighbour.
Yeah, that's very true. And well, I hate the expression, but using more joined up thinking, I think, is required. The issue often, a lot that in a practical sense, when the projects that we work on, we've sort of gone past that part of the process. We're given a specific project or an issue to deal with, and we come up with a solution, and we try and approach it at the largest scale possible to address, try and improve the condition of the not just the specific site, but the sections river upstream and downstream as well. But we're always having to work in a specific footprint. So that's something that I think really needs to be better integrated, I think, in land management and river management, is how to incorporate more understand the longitudinal connectivity of river systems, and how doing works in one area may not be of benefit to another area of the system. So we're also working in sort of larger scale projects of developing river management or river restoration frameworks, where we try and understand these issues of connectivity, so that we're prioritizing restoration and river management practices at the catchment scale. So we're trying to incorporate all of these issues of fragmented land ownership and river ownership. But it is definitely a problem. It's definitely a problem that you want to provide whatever solution to a problem in one area, but the adjacent landowner isn't that keen. What we have discovered in two rivers which we've done a lot of work on, we started off at one specific site, but then expanded upstream and downstream, is the Eddleston Water on the Scottish borders and the River Nith in East Ayrshire. And there, it wasn't, we can't take any acknowledgement or for the how this developed, but in both cases we've worked with other partners who over a large number of years have worked with landowners to try and engage them to bring them on board with the types of work that we're doing. So in both these examples, we started off doing restoration on one specific site, and over the years the adjacent areas started to sort of fall like dominoes, that other landowners, because they saw the advantages of what was happening, they voluntarily, you know, decided that, you know, their section of river was, you know, they wanted the similar type of work done their section of river. So it you know, that's sort of accidental in a way. It's sort of you know, appealing to sort of human nature, I think, sort of keeping up with the Joneses type of thing. They wanted, you know, the specific landowners wanted to see the benefits that their neighbours had. But it was a long process. In the case of Eddleston Water, it was you know, that project is still ongoing, and it's, you know, 10 years later, and we're still sort of chipping away at different landowners to try and get buy-in to these types of work.
Yeah, it's definitely, you can see how hopefully people will see the benefits, as you say, and sort of cotton on to it, and sort of allow you to develop them sort of further up and downstream, as you say.
Yeah.
So another question we've got here, are there any issues with water quality when putting sediment back into the watercourse upstream? Does this reintroduction of dredged material have to be done over a defined period of time to ensure suspended solids don't impact downstream?
In the case of where the example I gave, the Outlorgy, where we did that, not really. The sediments which were going back into the river had come from the river originally, so they, you know, they weren't contaminated. There was no issues of contamination, and you know, the material that went that was reintroduced, it was predominantly gravel and cobble, but there was sand and finer sized material there. There is a bit of concern about you know, putting sediment back into the river. Often we're advised that, you know, the sediment has to be cleaned and washed, and there should be no fine material. But that's not really reflective of natural sediment supply in river systems. When a river erodes into its banks or into sort of glacial terraces, it does naturally supply a large amount of fine sediment in. It's in terms of ecological damage or ecological, you know, damage to, you know, in-stream habitats. It's the very, very, very fine stuff like sort of topsoil, which in large quantities, which causes the problems. If you're reintroducing alluvial material, which naturally has, you know, sand-sized material in it, it really isn't a significant damage. It doesn't cause a significant problem. So the short answer would be no. There wasn't a requirement in the example I gave of considering the pollution issue. Although, you know, the pollution issue is a major, always a major concern in any project that we work on. We have to put in mitigation measures to prevent against, you know, the sort of transport of you know, fine sediment downstream. But if you, I always you know, if you go to any river system during a flood event, you know, and look at the color of the water, you know, there's a order of magnitude or orders of magnitude higher amounts of fine sediment moving through that system naturally than you'll ever introduce during the construction phase of a project. So I think there has to be a little bit of reality introduced into what the actual real implications are of fine sediments. I mean, obviously we need to consider things of actual pollutants and contaminants. That's a different issue. But in terms of fine sediments, it's not, you know, there's much greater benefit from putting, you know, the bigger picture is a much greater benefit than the sort of very localized potential detriment to you know, in-stream river health.
No, thank you for that. Another question we've got, sort of what modelling software do you use to simulate sediment transport?
I'm not really, well, I don't specifically do the sediment transport modelling. I know enough about modelling to be dangerous, but our modeler, Eric Gillis, or he's our technical director, Eric Gillis, he's the expert. But I do know that for sediment transport modelling, we use a bit of US code called SRH2D. It's got a really good sediment transport modelling component that's well, we've identified and shown as we've validated it on a number of occasions. So that's the one we use. I mean, I think most modelling packages, now have a sediment transport modelling component, but in terms of the ones that we've tried and tested, SRH2D it provides the best validation of output.
Oh, brilliant, thank you. So another one is regarding the use of large wood. Is the impact of growth of the trees, i.e. plantation deforestation, considered when looking at sustainability of scheme? Also, how long do these structures last? Would the wood break down over time?
Yeah, the second part of the question, the wood does break down over time, obviously decomposes, but in the type of environment it's in, the decay time is actually relatively long. It goes back to the question of what type of wood. We often asked what type of wood to use, for longevity, we would propose hardwoods, but they're much more difficult, or have been to date quite much more difficult to come by. So we do tend to use wind-blown plantation trees, softwoods, and we've only been specifically implementing these for around about 10 years, but that's not enough time for even softwood to decay. So there will be decay, but I've looked at or read some work recently on decay times of softwoods in river environments, and they do actually tend to be resilient for 30, 40, 50 years. The decay time isn't particularly, it's quite a long time it takes for them to decay. And the advantages of using large wood is, well, what we're trying to do with large wood is sort of kickstart the natural process. In terms of river restoration, we're using large wood to replace the effect that large wood would naturally have in a system, because large wood's been removed from systems because there's no there's not sufficient riparian forest. What we often tend to try and promote is, at the same time as using large wood for implementing large wood structures into the channel, is to encourage the regeneration of riparian woodland. And over the time scale that these large wood structures are decaying, we would have mature trees developing in riparian areas and naturally providing input to the channel. So we're trying to basically sort of provide the benefits before we sort of have the entirely natural processes reinstate. So yeah, we've never implemented we haven't been implementing these designs long enough to measure any significant deterioration of the wood structures, but inevitably it will happen. But the development of the channel, the development of riparian vegetation in the channels that we've been working on will counteract that process.
Perfect, thank you. So another one here we've got, just as with using hard engineering, are there any maintenance requirements attached to the use of large woods, and what sort of defects can we expect to get from the use of large wood?
Well, that's one of the reasons, one of the advantages of using large wood. It's a more sustainable approach, in that I wouldn't say that we're removing the requirement for maintenance, but we're certainly very much significantly reducing it. And in all of the large wood structures that we've put in, we've never had any fail. None of them have been significantly damaged by river processes. We've gone through a sort of learning process of how to implement these properly and to use the correct methodology to construct them. And there's been some examples, especially on the Eddleston Water, where we never got it right first time and we revised our design approach because we identified problems. But that was a sort of part of the learning process. And since we've refined these designs, there's never been a design that we've had to go back and fix. One of the biggest issues we had, and it's the reason why we put the coarse sort of cobble-sized material in the voids between the wood structures, is what we used to do initially was just reinstate the bank. The material had been excavated from the bank to allow the wood structures to be implemented was then put back in. And because the space between the logs was often quite narrow and the digger bucket couldn't get in between those logs, it couldn't pack down the material. So it was just loose topsoil going in between them. And as soon as the flow came up again, it would get in between the logs and it would just winnow out the space, the material between the voids and the wood. So that's why we put in the coarse material, was to avoid that. So we put in the coarse material up to the level of the top of the wood structures, and then topsoil can go on the top of that, which can get packed in, and then potentially a geotextile on top of that. So yeah, I mean, we've revised our methodologies to try and come up with approaches that are as sustainable as possible and don't require any sort of future intervention to try and for repair.
Thank you. Another question we have is, how does the short-term, medium-term and long-term cost benefit weigh up for natural sustainable watercourse management versus traditional engineering solutions?
Well, we haven't, I've not done any, or we haven't done any specific assessments on that. Typically, in terms of just costing the protection of a particular length of bank, the large wood structure approach is cheaper, but that very much depends on a local supply of appropriately sized wood and the requirement that you're not trucking it in too far. But in terms of the fact that it's sustainable and it doesn't require future intervention, it's ideally a one-off measure that doesn't need to be either reinstated or prepared. It's much more sustainable and cost effective in the long term. I mean, often where you put in the more traditional measures of bank protection, because it's reflecting or it's translating the hydraulic forces to the next area of unprotected bank, almost always at the margins of a section of bank protection, you'll get erosion starting up again. It'll just get moved down to the next location. So you've got to keep on extending the structure or putting in other mitigation measures. So using the large wood, it gets around that because you're more actively dissipating the energy. You don't get that same sort of translation of the erosive potential, and so you don't have to sort of keep on following the work downstream. You don't have to keep on implementing more and more work, or potentially not implementing the work and but having this erosion problem that continues for some time. So without, not having any specific figures to hand, the qualitative answer is that the large wood measures do tend to be much more cost effective in the long term, especially when you consider the fact that they're sustainable and don't require future interventions, or not nearly as much future interventions as potentially the sort of more hard engineered approaches. And also you've got the added advantage of them being much more environmentally sensitive. I think we did some work that Salix did in the past. The carbon footprint associated with a unit length of bank that was using a more traditional riprap type of structure compared to using the large wood type of measure, I think, I can't remember the exact figure, but it's something like 40 times more a larger carbon footprint per unit length of bank protection for the the more hard engineered option.
Thank you. We've got quite an interesting question here. So how do you deal with invasive species such as Japanese knotweed? And could you use that in natural bank restoration? Can invasive species enhance natural bank restoration?
I think on principle, no. I mean, by definition, we want to eradicate, invasives. I think it's a bit controversial to suggest otherwise. And again, it's not. Often we have to deal with invasives in our plant protection measures, but it's not often something that we explicitly have to deal with. We have to address the fact that there is invasives there, and they have to get dealt with independently of the works going in, and making sure that the ground's prepared sufficiently so that we're not going to liberate all the invasives to distribute them through the site. So it's definitely an issue we always have to address in any of these issues. So if we're doing some bank protection in a particular area, we'll do a survey to determine the presence of any invasive, just to make sure that the appropriate mitigative measures are put in place prior to the work's been done. But we certainly don't. We've never promoted the use of invasives to aid in bank protection.
No problem. Thank you for that one. So we've got final two questions. So the first one, you mentioned modelling the hydraulic performance of using large wood solutions as opposed to hard engineering to satisfy client concerns. How do you go about modelling complex bank structures like these? And can the cost of modelling offset the benefit, particularly in the client's perspective?
Sometimes modelling does become prohibitively expensive, depending on what the budget is for a project. And most of the time, we won't do modelling because of that reason. The implementation of the works is expensive enough for most clients, and providing some extra assurance of their stability through hydraulic modelling is an added cost that they can't justify. Where we do tend to do it is where the bank protection measures are, there's a significant risk to some important asset, for instance, high pressure gas pipeline or main supply, or water treatment plant, something like that, where we do need to show due diligence in providing the types of measure that are, we've identified are appropriate. So it depends on the perceived degree of risk and the available budget for these types of project. The types of assessment we do, I mean, they are, some of these structures are complex to model, and we're lucky enough to have Eric Gillis, who's an amazingly good and proficient fluid dynamicist. So we use combinations. I mean, what we've done in the past is use a 2D hydraulic model to understand the hydraulic forces acting around the specific log structures, and then using CFD to understand do the sort of force balances acting on the logs, individual logs, to resolve the sort of buoyancy and drag forces, to work out the level of engineering that we need to implement to hold those structures in place, and to make sure for the design flood they're not going to be moved downstream. So that will define either whether it's the degree of hard engineering that needs to hold those structures in place, whether it's cabling or some sort of hard structures holding them in place, or whether it's just a massive ballast to sit over these structures that we need to counteract those forces. So it is possible to do it. I mean, we don't often have to do that. As I said, it's only when we have to address some very specific issue, and there's some significant risk. We had to do it on one occasion in Northumberland, where we put these wood structures in to train the river to go through the centre arch of a listed bridge, but we didn't want the wood structures then to be mobilised and then damage the bridge. So we had to make sure and demonstrate that the wood structures were going to be stable. So we had to do this, CFD analysis on the wood structures just to ensure that we had enough ballast to that they were going to retain their stability for the design flood event. So I hope that answers the question.
Yeah, I definitely think so. Yeah, we've got a final sort of question. It's more sort of it's almost not really a question. It's just sort of looking at the riparian problems, and that this person's very happy to see that this is being discussed. The series issues are being discussed. So I'll just read their statement. In my LA, we have investigated in one team to engage with farmers and estate managers to not criticise them for flooding our highways or silt up SAC rivers full of crayfish, but rather assist them in field management and avoid soil erosion and nutrient loss. So they're just sort of happy that it's in discussion and it's being presented on today.
Well, it's really reassuring that these sort of things are happening, and I think it's a general. I mean, working in the industry now for a significant number of years, I definitely get a feeling that approaching things from a more sustainable way and considering the environment or in the broadest terms is becoming much more prevalent now. So working with natural processes and trying to reinstate natural conditions for, well, not just for the benefit of ecology, but that being one of the end products, I think is definitely increasingly evident in the work we're being asked to do, and considering the sort of rewilding type of approach, and rewilding using the loosest of terms, to try and it's the understanding that returning river systems to as close to their natural condition as possible is the most sensible and sustainable approach. Seems to be something that's really taking hold now.
Great. Well, given we've went through all the questions and really quizzed you then, it's just up to me to say thank you again for spending your evening presenting with us. Presentation was obviously very detailed, really diverse, and I think you've given a lot of designers, including myself, some food for thought about how we implement these kind of measures, thinking about more designing with nature and these kind of risk-based approaches, like you said out. So thank you again.
No problems at all. I mean, I was, I didn't say anything, but during the whole talk, the top sort of 10% of my screen was cut off, so I had to guess what the title of the slides was.
Well, you styled it out very well. Definitely not. Yeah, and it's always great with these presentations to see case studies and how those things, photographs, and how that all works together. It's something I personally found very interesting, understanding the different concepts you were talking through. So yeah, very, very knowledgeable, and thank you very much. So just from a SciWeb perspective then, just a few dates for people's diaries. We're, as a branch, we'll have a few more events upcoming in the next few while. So if you just keep an eye on our LinkedIn pages and on the SciWeb website, there'll be more details coming through, and kind of more general SciWeb international news. So obviously SciWeb declared a climate and ecological emergency at the end of 2019, and we've now got the 2 COP meetings coming up in 2021, both the climate emergency in Glasgow and the biodiversity COP15 coming up. So there'll be a few events and different things for people to get involved in the run up to those events. So that's something to keep an eye out as well. And in terms of other kind of CPD webinars from other branches and coming up in the next few days, March is quite busy for a number of events which are quite diverse and interesting, so I'd recommend checking out the events page online. But tomorrow there is a climate emergency in Ireland, a coastal perspective, which has been hosted by the SciWeb Northern Ireland and Republic of Ireland branch. So it should be an interesting one. And again, also on the 4th of March, there is an event being hosted by the East Anglican branch about water trading, obstacles and opportunities. So those are probably our two main things coming up. And then the next, another international event to note as well is the 14th of April 2021, the next session of Flood and Coast, which focuses on broadening innovative investment in FCARM, which is probably quite relevant to this as well, thinking about how we're going to carry more innovative approaches to things. And yeah, I think that's everything off the top of my head. But thank you everyone for joining and spending your evening with us and with Hamish's talk. And again, thank you to Hamish. And yeah, thanks for joining us. Everyone enjoy your evenings.